Okay, let's go to the closed pipe.
Okay.
Right, as always the case, the closed end is the node, open end is the antinode. The first one, we call it fundamental mode of vibration. Right, if you like, you can think of this as a displacement distance graph. Okay, so the closed end will be the node, open end, the antinode. A lah, should be able to write the A and the N there. If the length of the tube or pipe is L, for the fundamental mode or fundamental wavelength, fundamental frequency, whichever you want. Right, remember this is a quarter. So we call this first one lambda 1 quarter equals to L. So lambda 1 take the 4 across there is 4L. In terms of frequency, F1 is V over lambda 1. Lambda 1 is 4L. So V divided by 4L. Okay, so as always is the case, if you are having a problem how to draw, right? Draw the waveform first. Sketch the waveform, sine waveform, and then start with a 0. Start with a 0. That's a closed end. And then to a maximum or minimum. Are you louder?
No, it's okay. I'm not.
Oh, because I heard some voices. No, anti-node. Okay, so start with that. So that will be your. Sorry, it should be a quarter, not half a wavelength. You can see that I'm very careless. Didn't pick it up.
Yeah, I can see.
Okay, so it's a quarter. Okay, so that's the first one. 0 to a minimum or maximum, doesn't matter. So that's a quarter wavelength. You can call it lambda 1. And that's your wavelength. That's a quarter of a wavelength. And the next one, the second mode will be from 0 to another. Right? We pass this maximum already. The next one will be this maximum. Right? We go to the minimum and maximum there. Okay. So closed pipe. You can roughly divide into three equal sections. And easier to draw from 0 to maximum and then to minimum. And then the other side also the same, from 0 to minimum, 0 to maximum. Okay, and then you should be able to say, okay, this is half lambda 3, this is a quarter lambda 3, so add up is 3/4. So just now earlier we have our F1 is B over lambda 1. So lambda 1 is just your right? That's your F1 just now we have got earlier. Now we come to our second overtone. Don't worry about the term because sometimes can be very confusing. Different book will call it differently. I don't think they are very cruel to text you on that. Text you on that. Okay, so this length is 3/4 lambda 3. Or lambda 3, take a 4 across there, take the 3 down, 4 over 3L. And F3, right? We don't have F2, so we call it F3. V over lambda 3, V over, right? That's your lambda 3. So we times 3 here, times 3 the numerator and denominator times 3. Cancel the 3 here, so we got 3V over 4L. Okay, V over 4L. Right? This is your F1, V over 4L is 3F1. Any comment or anything that is not clear?
Why is it that can 2F be like in there or 2F is not possible?
2F is not possible. Usually we call
Oh.
it F3 rather than F2 lah. So for a simple reason that it's easier to give a general statement later on lah. There's no others already. Only this one, right? Only this one and that one that's possible. The next one will be this one. So make sure you know how to draw at least these three. Okay or not?
Yeah, understood.
Right? I summarize for you for all the three of them. Right? So in general, same as the string. Right? Fn and F1. N stands for harmonic, right? If you like, what numbers are? The N, the first harmonic, the third harmonic, the fifth harmonic. Right? In terms of wavelength, then it's lambda 1 over n, no? Same thing as a string or open pipe, except this is odd, that's all. N is odd. Okay, so these are just summarize for you what we have just learned. And if you compare string with open pipe, they are the same formula. Right? Closed pipe is different, slightly different. And V over 4L. Right? Smaller fundamental frequency is smaller. Okay, we can compare that, closed and open pipe. Sometimes they require to, yep.
Mr. Ku, can I see the previous slide, please?
See the what?
The previous slide.
Oh, previous slide, okay.
The slide before that.
Slide before this one.
Oh no, before that. Yeah.
Before that some more.
This one. Yeah. This one. Okay. Thank you.
Okay, so especially objective one, they will test you lah. Fundamental one, you need to know the formula. Right? V over 4L. Fundamental for open tube is V over 2L. And what summarize that, you can get it from the internet. This is from the internet. Okay, experimental wise, we can use this setup. This can be a burette. This can be a reservoir.
Okay.
All we need to know is note the value of the tuning fork. Then lower the reservoir. And when you hear the first sound, then there's your L1. Then you lower again. You hear the second sound, that's your L2. Okay, then after that, we can go to the physics involved, how to determine your wavelength, your sound. Okay, this one came out in 2006, June. We will do it. We'll go over with you first. Then we'll go solve the problem. It's your L1. And L2, you know how to draw. Right? They will probably ask you to draw on the diagram itself. They give you the value. Right? So this is a quarter, L1. Normally, we cannot use this one to calculate the wavelength. For simple reason, there's an end correction there. That means you don't need to know about end correction. Right? That's not in the syllabus, but I thought bring it out. Because 1 year it just came out, end correction, but they didn't call it end correction. The reason why is because at the free end there, it can vibrate freely. So the antinode is slightly above the top of the burette. That's why we have what you call the end correction. That's the E. Okay, so that one you should know is 3/4. Right? Remember, we are using the same frequency or the same wavelength. Previously, we used different wavelength. Here we use the same wavelength. Right? But this is 3/4 wavelength. 3/4 wavelength. L2 plus E. Then you subtract, you get this answer. So normally they will require you to memorize the formula. If you can, you can. If you cannot, then derive it. But remember, there must be an E there. An E there, and E for end correction. And then when you subtract that, L2 minus L1, that will give you 32.4 cm. That's your half lambda. Right? Difference between progressive and standing wave. Displacement at the nodes is permanently 0 for standing wave. Amplitude, each point along the wave have different amplitude of vibration from neighboring points. Right? Any point along here, they have different amplitude. They are in phase, but different amplitude. Phase, at points between successive nodes, the vibration are in phase. Successive nodes will be here. They are vibrating in phase here. Same as here. Right? They are vibrating in phase. Energy stays at the same position along the medium. Right? You are required to memorize a few of them, at least 2 or 3 of them. Progressive wave, no points are at 0 displacement permanently. Right? Maybe 0. After that, it has a displacement. Amplitude, at every point vibrates with the same amplitude. That means they may be different displacement at different time, but ultimately the amplitude of each point is the same. Phase, the phase of neighboring points are all different. Right? They are all at different phase of vibration. Energy, the wave energy move along at the speed of the wave as the wave progresses. Okay, so that summarizes for you here. If you can remember DAP, the rocket, DAP. Any question before we go further?
No.
This one is memory work only. Nothing can be done. Okay. The black one is the displacement of air particle. And then the red one will be the air pressure. Sometimes they will ask you to relate with air pressure. So where the close end there, it cannot vibrate. So all the particles will be accumulate there, will be slightly up. This is atmospheric pressure, the line there. And this one is above atmospheric pressure. That part is below atmospheric pressure, that part there. And then that part is above atmospheric pressure. Okay, that's just a variation with pressure. Okay, vibration of air particles in open pipe. Right, remember sound wave are longitudinal wave. First harmonic shows the displacement distance graph.
Sorry,
Okay, anything?
Yeah. No, it's okay. I'm fine.
Okay, Displacement of sound wave is horizontal. Remember, it's vibrating this way as the wave travel along here. That's what I mean by longitudinal wave. Taking upwards as and to the right as positive. Usually we'll take upwards as positive, to the right as positive. The arrow show the displacement of the particle of the air either all pointing to the node or all or away from the node. Right? So if we take this part, the blue one, then it's moving to the right of maximum here, and then this part will be smaller. This part will be smaller still, and the node is not moving at all. Then this part is negative, right? Smaller, smaller, larger, larger, the particle here, larger but vector, open end, larger still, the largest. Okay, any
No.
anything not clear?
No. I'm fine.
Yeah, fine.
Yeah.
So if we look at the red one, the red one will be negative direction. Right? This is smaller displacement, the particle here, small displacement. This one even smaller still. And then at the node there will be 0. Same. After that will be positive at this point there, which is here. And then this point here, slightly longer vector vibration. And then this will be the largest. Okay, or sometimes they will draw it two together. Usually exam come out will draw it one side only, not two sides. Okay, I think we have completed this part. Okay, let's just try some question. Okay, what's the answer for this one? What is the wavelength of the standing wave formed in the open pipe? Length of the tube is 30 cm. Can?
20 cm.
Right, that is your, if you look at the top one, that is one wavelength, is another half, so it's 1.5 wavelength equals 30, the lambda is 20 cm. Can?
Yep.
What is the wavelength of the standing wave formed in a closed pipe? If the length of the tube is 30 cm, here to here, half a wavelength, another half. This one is a quarter. Right, so this one wavelength plus a quarter wavelength equals to 30 cm. So what's the answer?
24 cm.
So that's your wavelength. So it's 5/4 lambda equals 30 cm. Okay, good. Answer is A. Depends the computer is a bit capable. Okay, let's try one past year question. This is the one. 2006 June. A long tube fitted with a tap is filled with water. A tuning fork is found above the top of the tube as the water is allowed to run out of the tube as shown in figure 6.1. Right, they draw for you. This one they require to draw yourself. So if this is the first mode, then this is the second mode. And then you should know the physics that we have done just now, earlier. Okay, a loud sound is first heard when the water level is as shown in figure 6.1, and then again when the water is shown in figure 6.2. Figure 6.1 illustrates the stationary wave produced in the tube. Figure 6.2 sketch the waveform of the standing wave set out in the tube. You are required to do that. That's what we are doing. That's the second part. And then mark the node, antinode, node, antinode. Okay, I will send you the video. I'll send you the video. The frequency of the fault is 512, and the difference in height of the water level for the two positions where the loud sound is heard is 32.4 cm. Calculate the speed of the sound in the tube. Okay, so you have to, from here, half lambda 1 equals to the difference. Can or not? We are just using that lah. If you are using the original calculation, half lambda is that different. Okay, And from there we cross multiply lah, times 2 to get this value, lambda. And then speed is frequency times wavelength. You need to memorize this formula. And frequency is given, wavelength is given there, and that's the 2 here, and that. Length of the air column in the tube is figure 6.1 is 15.7 cm. Suggest where the antinode of the standing wave is produced in the tube is 6.1, likely to be found. Right? Even though it's not end correction, that's what it means by end correction. It's not at the top there, it's slightly above there. So you have to subtract. Find your lambda is 0.6, that's your lambda, 0.648. So the first mode is a quarter. So you can subtract. So 16.2 minus 15.7 is 0.5. So it's above the top of the burette. This is 2006. Remember, this is your L1. L1. Okay.
The end correction is supposed to. What is the end correction supposed to be?
Usually, you don't need to know end correction, but actually, the vibration is not at the top there. It's slightly above the top because the free end can vibrate freely. So that's the reason why you have an end correction there. Just go back to. Right? Usually, it's not like what we draw there lah. It's slightly above there, the antinode. So that is your E lah. That's what we calculate just now, E. But it's, as I said, they don't require to know end correction. That's why they didn't call it end correction. They just ask you where is the starting point. Right? Where's the antinode? It's not at the top there. It's slightly above the top there. Try this one. A standing wave is set up in a stretch string as shown. Which statement about the points in the string is correct? What's the answer?
Point Q vibrates with the largest amplitude. A. Oh wait, no. Oh, sorry. No. That's not true. Sorry.
Ken?
I think I would say
Okay, let's look at the answer. Q vibrates with the largest amplitude. No. Right? Not Q. Sorry. Right? R largest amplitude, not Q. Points P and R are vibrating in phase. P and R, they are in phase. R and Q are in antiphase. Right? Don't get caught. This is phase, not amplitude. They are different amplitude, but they are in the same phase. This one and this one is phase. This one and this one is 180 degrees out of phase. S is the node, not antinode. Horizontal distance between R and S is a quarter, not half. Ken? Anything not clear?
no. I'm clear.
Okay, Okay, this is one of the questions that came out in the past year paper, 2007 June number 5. What's the answer? Right? What is the wavelength?
I'm still doing. I would say the wavelength is 13 cm.
Okay, let's calculate out and see whether you're right or wrong. Right? Just draw. Right? This is the node there. There's the node there. Right? The antinode is between. So draw the waveform. Right? So it's one wavelength here, two wavelength. Sorry, from here to here is one wavelength. From here to here is another wavelength. This is half a wavelength. This is 2.5 wavelength equals 39 cm. The wavelength is 15.6 cm. Okay or not? Okay, looks like we have to change another Zoom late soon. Then we got 10 minutes. If the frequency of the vibrator is 2000 Hertz, what is the speed of the sound?
Uh, 312 meters per second.
Yeah, we calculate the wavelength already. Have the frequency, so have to calculate the speed.
Yeah, 312 meters per second.
Okay, frequency times wavelength. That's a wavelength, change it to meter. That's a frequency, 302 meter per second. Okay, this microwave, have a go at it. What's the answer? This is the 90s, that's why I got up to E. Pass your question also. Can?
Wait,
There's a 0, 0 at R, 0 at S, 0 at T. So calculate the wavelength first.
okay.
Right? Just draw the diagram, no? The standing wave, that's the standing wave.
Yep. I I think it's one. It's D. I think.
Right? Speed, you use the speed of light. Right? Only at the nodes are the intensity 0. So at the nodes, the displacement is permanently 0. That's why you got 0 here, 0 here, 0 here, and RST. Right? So RT is your 3 cm. Then use speed is F times lambda. Right? Put in there, calculate your frequency. Okay or not?
Yep. I understand. I got it.
Try another one. This one.
Okay.
What's the answer?
Uh, E.
Okay, let's see. Right? Remember, there's a fundamental mode. There's your half lambda equals to L. And then the speed is F lambda. So you replace your lambda. Right? lambda here with V over F. V over F equals to L. V is a constant, half is a constant. So we take our F across there, we got LF is a constant. Easier lah, rather than go and calculate your V and then calculate again, all that. Then L1, F1 equals to L2, F2. As long as we got this formula, then we got L1 is the first one, 100. F1 is this one. And L2 is what we want to find. F2 we are given is, sorry, L2 is 400. 400. And F2 is the one we want to calculate. We call that F. Calculate one, answer is E. Okay.
Okay.
I think I'll give you 5 minutes break since our Zoom is almost over. And then we will start 5 minutes time now.
Okay.
A new topic. Okay, you there?
Yeah. Sure.